Let us start. Today in our SIM lab, we are repeating, of course, what we have told you earlier. Now I am telling you again or discussing again the torsion test. And along with my notes about the torsion rule, I will share the video of the lab and torsion test in my lab, as well as a few videos downloaded from YouTube. Now, you know what I have discussed in earlier classes, always I have told you at the beginning, there are few standard tests in strength of materials which are used, which are pretty old in their due to at the time at the angle of their creation, but they are using for years. Still today they are useful, and possibly in the future they will be also useful. This is the standard test used in industry, in research labs, in all these institutes to verify, check, and verify, and for find out certain properties of the materials which are being materials or items or raw materials which are being used for manufacturing different items in our workshops, in our structures, and in any other manufacturing area. In order to use them during manufacturing, we are supposed to know a few of its properties, like say its hardness, like say its tensile strength, compressive strength, impact strength, torsional strength, etc. Because you have to supposed to know this test, because all the machine members which you have manufactured or you use, all the parts which will manufacture, all the structures which will use for your constructions, will require to know the concerned member strength, member torsional rigidity, your impact rigidity, its hardness, etc. In order to know the same, you have to do certain tests on this concerned beam members. The question is one, these members cannot be directly used for the tests because all these tests are destructive nature. Means this test destroy or breaks the test piece which is stretching. So you cannot use your original machine members for breaking or only simple for test. So how will you test it? We will make a standard specified test piece or work piece or specimen, which will be used for breaking and checking the strength or toughness or hardness of the concerned materials. This test piece will have a different specific shape and dimensions, and as per design given by the concerned testing processes. These are all the standards given, and every machine is supposed to give you. All the machines are to torsion, tensile test, impact test. They have a different type of different capacities, but all of them will give you a support, a standard size and dimension of the standard dimension of the test piece, which they are supposed to test in the particular machine itself. So everywhere, every machine, so you should have a separate unique test piece, which we manufacture separately by the same process as your original or the member under consideration will do, so that you can check this impact by checking this or checking this impact of this test piece. You can check the torsion strength by checking the torsion stress of the test piece, etc. So Here in the torsion test, we need a specific test piece to check, and we need a specific machine to do the testing. And let us discuss the operating instruction for torsion bearing testing machine. Now, the machine is designed for torsion and twist test. Means, what is the difference between torsion and twist? It is nothing. There are different items for torsion, which different names this torsion can be dealt. It can be torsion, it can be twist, it can be couple, it can be movement like this. But they are basically they are same. They are two forces of same magnitudes are acting, not in the same line of action, but in parallel but opposite line of action on a particular machine member, which is twisting or rotating or twisting this concerned machine member, and we are supposed to find out how resistant this concerned machine member against this twist. Now, this test can be used for round, flat strips, and tube specimens. But generally, we will use round pieces. We will not go for strip or flat specimens. It is operable on electrically, of course, by means of a 415 volts and three-phase 50 Hz electric supply is required for its input. Now, torque measurement is given. A torque measurement electronic torque transducers. This torque transducers is applied to the fast specimen by gearbox through reduction gearbox assembly. So torque is supposed to be applied we will get the power and we'll fix the machine, fix the torque test piece between two vices. So one vice is fixed and another vice is rotating or twisting the material. And this rotation is achieved by means of a gearbox through reduction gearbox drive. Thus, the construction of the machine is that we have a measuring panel, a driving unit coupled to it. So it is as a driving unit means like it's a motor and gearbox, and a measurement panel which is here we have an electronic transducer which will measure the amount of twist which we are applying on the machine, and what is the final twist and how we will step it, how we'll keep the last value unsafe saved on the machine. I will discuss in course of time. The measuring panel here, where in this machine houses an electronic microprocessor-based digital electrical unit. So microprocessor digital electronic unit here means digital means its numbers are shown in the figure, not we have to write down or measure it. That is within the digital display and indicated as an indicator device, and it is Microsoft processor based. Now, what is the driving unit here? The driving motor, just a second. A driving unit is a geared motor, is fitted on the reduction gearbox. The drive from the motor is given to the one shaft through a chain sprocket drive. The one shaft is supported on the gearbox out. So what we have here, it's a driving motor. We have a geared motor. Geared motors is under outlet of the gear. We have a geared system and which runs through a reduction gearbox, which runs a also outlet is running a reduction gear from unit. The drive formula is to keep the one shaft through a chain sprocket drive. The one shaft are supported by gearbox housing. So first of all, the motor is given the workshop a chain sprocket drive through a chain sprocket drive. Drive from the motor is given the one shaft through a chain sprocket drive. One shafts are supported in the gearbox housing. A trolley mounted on the 4 ball bearings travels over the base of frame bed for adjusting the length of the system. A trolley is supported on 4 ball bearings. Bearings travels over the layers of the frame bed for adjusting the length of the system. Now, the digital display indicator display that talks in bright digital display. Now, what is the theory behind it? A torsion test is quite instrumental in determining the value of the modulus rigidity ratio of the shear stress to shear strength in a metallic specimen. So what we are doing here, we are going to calculate the modulus of rigidity analytically. What is defined as the ratio of the shear stress to divided by the shear strength. The modulus of rigidity can be through observation made during the torsional equation. T divided by IP is equal to C into theta divided by L. C into theta divided by L, or C is equal to T into L divided by IP into theta. Where T is the torque applied, IP is the polar moment of inertia, C is the modulus of rigidity, and theta is the angular twist of the result gauge length. So C is the modulus of rigidity is given by T into I divided by IP to theta. T torque applied, I polar moment of inertia, theta IP. IP polar moment of inertia, L is the length, and L into length, and L is the gauge length, and C is the modulus of rigidity, and theta is the angular twist. Now, what we are going to do this test is, the machine on the end of the specimen are held in suitable grips through one of the torque through which the torque is applied. So we have two vices on the machine, and it is supposed to be grip the workpiece, and one vice is fixed, another vice is rotating, which is applying the torque over the machine. Other end is applied, other end is attached to the torque arm by means of which the torque of the specimen is measured. Other end is now attached to the torque arm by means of which the torque of the specimen is measured. The torque arm is attached to the indicating unit through the intermediate gear housed in the cabinet. Now, the digital indicator is indicating the torque developed due to the twist of the specimen. So what we have here, it has a pair of vices, and those who houses and fixes the end of the specimen with both the ends, and one of the vices is fixed, another vice is twisted, and through which the torque is applied. Another this torque arm with the torque of the specimen is that the torque arm is attached to the indicating unit through the intermediate lever housed in the cabinet. Torque arm is attached. The digital indicator is indicating torque developed due to the twist of the specimen. Indicating torque developed due to the twist of the specimen. So, a process. The digital indicator displays the torque in bright digital display. A torsion test is quite instrumental in determining the value of the modulus of rigidity and of the metallic specimen. The value of the modulus of rigidity can be found out through observation made during the torsion equation. T into IP is equal to C into theta by L, or C is equal to T into L paired by IP into theta, where T is the torque applied. Now, IP is the polar moment of inertia, and theta modulus of rigidity, theta angle of gauge length. The operational procedure is that place the machine on the solid level surface. You should have a proper bed and for solid bed, and where the machine is placed and clamped and gripped to the bed, as well as it should be properly level. Then you should supply give 415 or 420 or 440 volts, 3-phase 50 Hz or AC, supplied to the machine from the mains of the mains. Clamp the workpiece with the machine at both the ends. Test specimen are having height up to approximately 800 millimeter approximately can be tested in the specimen machine. A round specimen shall be tested in the shape of a dumbbell. Measure the diameter of the workpiece at least 3 different positions. Set the digital torque display to 0 position. Set the round graduated scale to 0 to the negative point. Turn the electric lever control switch in reverse direction to activate the driving chuck. With this, the test specimen starts twisting, and at the increase in load, the display on the digital load indicator presses progressive slide digitally as well. On the electrical level, so first what you have to do, that specimen have a certain length, clamp the workpiece in the machine both the ends. Now there is a two vices in the workpiece. It is by vices is fixed by has two clamping bolts on each of them, and which fixes the workpiece. Workpiece ends is like a dumbbell shape item, and whose ends are like a square cross sections, and body is the round cross section. And this workpiece, the ends are totally embedded inside the hole of the vise, inside the hole of the vise, so that only twist is happening only on the round piece of the specimen. Now, this the workpieces are put inside both the vices, and by means of the clamping or tightening the bolts on both the sides, in left and right side, we will have the fab which are supposed to fix the workpiece to the machine. Next, this specification is supposed to have a approximately 800 millimeter length and can be tested in the machine. The round specimen should be tested in the shape of a dumbbell. This specimen is actually round, but it's tested in the shape of a dumbbell. Measure the diameter of the workpiece in at least 3 different positions. Set the digital torque display to 0 position. Measure the diameter of this in at least 3 different positions. Set the digital torque display to 0 position, first of all, and we have to check the length of. So set the digital display to 0 position, set the graduator scale to 0 to the indicated point, and set the indicator P, actuate the indicator P by pushing the value of P in order, which is nothing but keep the final reading on the reading as fixed, and it will go back. It will not go back to 0 position, which will help us to record the readings. Now, the ground graduator scale, which is on the side of the rotating vices, we set it to 0 in order to know the amount of rotation which will apply before breaking the vice. Turn the electric level strip in reverse direction to absorb the driving charge. To this, specimen starts twisting properly, and with increased load, the load display load indicated progression in quickly digitally. Now coordinate the rotation, twist the job in the forward direction, and takes the reading of the torque after a definite interval. Continue the rotation and twist the job, twist the job in the forward direction and get the reading after reading of the torque as well as reading of the reading of the rotation or amount of rotation applied after a definite interval. Next, consider the process till the workpiece breaks. Next, put a torque in one side and another twist, exercise the twist. Reading read of the coordinates of the convenient point of the straight line position angle, torque to it, and calculate the value of C by using the pattern. So, if of a convenient point, get out from the straight line portion of the torque twist curve, then find out a convenient point and calculate the value of C using the relation. The angle twist method degree should be converted in written and before plotting curve. When the machine is not in use, another clerk and clipped in from the machine. Now, this is more or less the deflection. Let us go through the torsion test and in which I have those videos I have taken in the laboratories. This is a torsion testing machine which are having a vice at left end and a vice at right end for holding the workpiece by fixing it by means of two sets of bolts as seen. And the vice at the right hand side has a graduated scale like this, which will give you the graduation from 0 to 360 degree while rotating the vice. The vice will rotate and twist the component, twist the item which is fixed between the points, and this amount of torque thus released will be available from this digital load display device. And after sufficient number of twists, the vice, the block will broken, the rod will break, and showing you the breaking torque or twist of the item itself. And this vice will give you the amount of twist required to break this particular workpiece. This is a destructive device, so you have to use and throw it out. You have to use, break and throw it out, and is made from the items whose torsion strength you want to manufacture, check. This is a gearbox and a motor and a chain drive through which this vice is rotating, through which reduction is vice is rotating and showing you the number of twists. And this twist and torque is required to know the radius of gyration of the particular item which you are checking. I'm just repeating the same. Here in the Rockwell this is a torsion testing machine which are having a vice at left end and a vice at right end for holding the workpiece by fixing it by means of two sets of bolts as seen. And the vice at the right hand side has a graduated scale like this, which will give you the graduation from 0 to 360 degree while rotating the vice. The vice will rotate and twist the component, twist the item which is fixed between the points, and this amount of torque thus released will be available from this digital load display device. And after sufficient number of twists, the vice, the block will broken, the rod will break, and showing you the breaking torque or twist of the item itself. And this vice will give you the amount of twist required to break this particular workpiece. This is a destructive device, so you have to use and throw it out. You have to use, break and throw it out, and is made from the items whose torsion strength you want to manufacture, check. This is a gearbox and a motor and a chain drive through which this vice is rotating, through which reduction is vice is rotating and showing you the number of twists. And this twist and torque is required to know the radius of gyration of the particular item which you are checking. The job is now broken due to the rotation of three complete rotations in 360 into 3 plus around 90 degree
means 360 into 3 plus 90 degree rotation, and the tonnage required for breakage of this workpiece is given as 4.49 kg meter, at which is showing the peak workpiece, peak tonnage of the workpiece. Thus, the operation is this as complete. Let us start the torsion testing about this torsion testing device. We have fixed the workpiece between these two vices by screw, and we have the display device is showing plus 0.001, which will give us that breakage torque when this workpiece will break. Now we will start operation of the machine by rotating it on clockwise direction. This will make the workpiece rotation between the two vices, and as well as the rising of the torque over the load display devices, and it will go on rising and unless and reach to a stable position. Afterwards the material will break and show you the final result itself. Here we have to choose we have to select the readings of these dials at which the IC's job is broken, and we have to select this load over the breaking load from the digital display device itself. Thus the operation will be complete, and these two values will be used for to calculate the radius acceleration of the workpiece itself. Thank you. Let us start the torsion testing about this torsion testing device. We have fixed the workpiece between these two vices by screw, and we have the display device is showing plus 0.001, which will give us that breakage torque when this workpiece will break. Now we will start operation of the machine by rotating it on clockwise direction. This will make the workpiece rotation between the two vices, and as well as the rising of the torque over the load display devices, and it will go on rising and unless and reach to a stable position. Afterwards the material will break and show you the final result itself. Here we have to choose we have to select the readings of these dials at which the IC's job is broken, and we have to select this load over the breaking load from the digital display device itself. Thus the operation will be complete, and these two values will be used for to calculate the radius acceleration of the workpiece itself. Thank you. The job is now broken due to the rotation of three complete rotations in 360 into 3 plus around 90 degree means 360 into 3 plus 90 degree rotation, and the tonnage required for breakage of this workpiece is given as 4.49 kg meter, at which is showing the peak tonnage of the workpiece. Thus the operation is this as complete. The job is now broken due to the rotation of three complete rotations in 360 into 3 plus around 90 degree means 360 into 3 plus 90 degree rotation, and the tonnage required for breakage of this workpiece is given as 4.49 kg meter, at which is showing the peak workpiece, peak tonnage of the workpiece. Thus, the operation is this as complete.
Let us go for some more videos downloaded from YouTube.
In this video, we're going to look at how we can take our data from our torsion test in order to determine the modulus of rigidity of our material. So where this might be useful is if you had some test data and you wanted to determine what the likely material was that was used in the test. If we can determine the modulus of rigidity, which is a property of a given material, we can then go some way to determining what the material was that was involved in the test. In the example we're going to look at here, I'm going to use the test data that was obtained in a torsion test for 0.4% carbon steel. And if you haven't already done so, you can go back and watch that video in order to see how the test's conducted and how the results are collected. So to begin with, what we have is the angle of twist that the specimen is being subjected to. Now, in the practical demonstration, we discussed how the machine would produce an audible click for every partial revolution of the shaft. And we also talked about how each of those clicks, or how each of those partial revolutions, was equal to an angle of twist of 0.3 degrees. Now, as we know from an earlier tutorial, in the general torsion equation, the angle of twist must be inputted in radians. So the first thing that we need to do is take each of our angle of twist in degrees and convert them into radians. Now, the simplest way to think about this conversion is we need to multiply by the number of radians in a circle and then divide by the number of degrees in a circle. So to input a formula, we need to start with equals. We need to click on the cell that we're converting from degrees to radians. We need to multiply by the number of radians in a circle. So Shift 8 for multiply. The number of radians in a circle is 2 pi. So we need to do 2 times pi, and there's actually a function for pi, pi, but we need to remember to do open and close brackets in order to input that value of pi. So far we have the value in degrees times 2 pi, which is the number of radians in a circle, but then we need to divide by the number of degrees in a circle. Well, the number of degrees in a circle is 360, so divide by 360. So times 2 pi over 360. We can then copy that formula down. And that will populate that column for us. Now, if you're not comfortable with the conversion there, then you could have done the conversion of times 2 pi over 360 in your calculators and then multiply each of the values in this column by that conversion factor. 2 pi over 360 is actually 0.01745, so you have the option to do it that way if you prefer. But since we're using Excel, we may as well use the functions that are available in Excel. Okay, so now we have our torque values that were required in order to achieve those angles of twist. And the final column is the stress that's acting on the sample. Now, we know from an earlier video that the stress from the general torsion equation is T times R over J. So on the right-hand side here, I have some data for our test piece. the test piece had a diameter of 6 millimeters and a length of 80 millimeters. But what we're going to need is the radius in meters and the J value in meters to the fourth. We need those both in SI units. So in order to determine our radius in meters, we need to halve the diameter, giving us 3 mil, and then divide by 1,000, giving us 0.003 meters. And for our J value, we're going to use a formula. And the formula for the J value for a solid shaft is pi d to the fourth over 32. Again, we saw that in the earlier video on applying the general torsion equation. So equals pi, well, we've already said we can input pi by doing pi, open brackets, close brackets, times the diameter to the fourth. Well, we have the diameter in millimeters, 6 millimeters, but we need to input that diameter in meters, or 0.006. And we need to raise that to the power 4. Well, to the power of in Excel is shift 6. And finally, we need to divide all of that by 32. Now, the way I'm going to do that is by putting a bracket in front of pi. I'm going to put a bracket after to the power 4th, and then do divide by 32. So pi d to the 4th over 32 gives us a J value of 1.272 times 10 to the minus 10 meters to the 4th. So now we have everything we need to calculate our stress, because stress is T times R over J equals, we need to click on the torque value, because as the torque value changes, the stress changes. We know the radius is 0.003. Alternatively, we could have cell referenced H3 there. And our J value, here I'm going to use the cell reference, divided by H4. Now, when we paste that formula down, we don't want H4 to change to H5, H6, H7, and so on. So what we need to do is absolute cell reference this H4. And the way that we do that is by putting a $sign in front of the H and a $sign in front of the 4. I'll show you what this does in a moment. So let's copy this down a few cells. And we can see the value of stress is increasing. If we click on a later cell, here, you'll notice that the value of D3 has changed to D6, but the absolute cell referenced value of H4 has remained as H4. Now we do have one more modification to do here, because I've calculated the stress in pascals, and we actually want that in megapascals. So to get from pascals to megapascals, we need to divide by 1,000,000. So here, in my formula, I'm going to put a bracket at the start, a bracket at the end, and I'm going to divide by 1,000,000. So divide by 1 with 6 zeros. 1, 2, 3, 4, 5, 6. And now I'm happy with that. I can paste that formula down to the bottom of the column. Like so. Now, when the test was carried out, some data was missed. So what I'm going to do is just remove these sections here for the missed data, as otherwise that would impact on our graphs. And I'm going to plot two graphs. Now, the first graph that I'm going to plot is angle of twist against torque. Now recall that the general torsion equation came in 3 parts. T over J equals tor over R equals G theta over L. So T over J equals G theta over L. I'll just make a note of that over here. So let's plot the graph and see what we're left with. I'm going to highlight the 2 columns. I'm going to do insert, scatter, and I end up with a graph that looks something like this. Now this graph represents all of our data, but in actual fact, we can only determine the modulus of rigidity during the elastic deformation stage. So the first thing that I'm going to do is I'm going to amend my angle of twist axis at the bottom. So if we click on Design in the menu at the top, and if we go to Quick Layout, then we can choose a layout that includes our legends. Our x-axis is angle of twist in radians. And our y-axis is torque in Newton meters. Now, just so we have a little more space here, I'm going to remove the title. So we can see clearly here that the elastic deformation is complete after considerably less than 1 radian in terms of angle of twist. So let's modify this axis. We have right-click, Format Axis, and let's set the maximum value on that axis to 1. Okay, so as we inspect this further, we can actually see that all of the elastic deformation is complete within the first 0.2 radians of twist. So let's modify that further. And we'll set that at 0.2. Okay, so our graph looks a lot different now. And what we